Problem 24, Quantum Mechanics. The question is, the differential scattering cross-section d sigma by d omega for the central potential V of r equal to beta by r e raised to minus mu r, where beta and mu are positive constants, is calculated in the first born approximation. Its dependence on the scattering angle theta is proportional to. So in the question, the dependence of the differential scattering cross-section d sigma by d omega on the scattering angle theta is asked. The potential given is V of r equal to beta by r e raised to minus mu r. Now using the first born approximation, we can calculate the scattering amplitude f of theta. Once you have f of theta, now take the modulus and square, that will give the differential scattering cross-section. Now from the differential scattering cross-section, we can find out how it depends upon the scattering angle theta. First, let us write the equation for the scattering amplitude, that is minus 2 mu by h bar square q integral 0 to infinity r V of r sin q r dr. The equation is for spherically symmetric potential. Now we can use the equation because in the question the central potential V of r is equal to beta by r e raised to minus mu r is given. The given potential is V of r is equal to beta by r e raised to minus mu r. That is f of theta is equal to minus 2 mu by h bar square q integral 0 to infinity r. Now instead of V of r, write beta e raised to minus mu r by r, then sin q r dr. Sin q r dr. That is equal to minus 2 mu divided by h bar square q. Then we can take beta outside. Now integral 0 to infinity e raised to minus mu r sin q r dr. Now we have the expression e raised to sin theta is equal to e raised to I theta minus e raised to minus I theta divided by 2i. Now using this equation, we can write the expression for sin qr and substitute in the equation of f of theta. Therefore, f of theta is equal to minus 2 mu beta by h bar square q integral 0 to infinity e raised to minus mu r. Now instead of sin qr, write e raised to iqr minus e raised to minus iqr divided by 2i into dr. Now f of theta is equal to minus 2 mu beta divided by h bar square q integral 0 to infinity e raised to minus mu minus iq r minus e raised to minus mu plus iq r all divided by 2i into dr. And that is equal to minus 2 mu beta by h bar square q integral 0 to infinity. Now after integrating, you will get the result as e raised to minus mu minus iq r divided by minus mu minus iq minus e raised to minus mu plus iq divided by minus of mu plus iq. Now the limit is from 0 to infinity. There is a 1 by 2i factor missing. Actually f of theta is equal to minus 2 mu beta by h cross square q into 1 by 2i integral 0 to infinity e raised to minus mu r e raised to iqr minus e raised to minus iqr dr. So let us include the missing 1 by 2i there. Now we have f of theta is equal to 1 by 2i minus 2 mu beta by h bar square q into the value of the integral. That is minus mu b by h bar square qi. Now after applying the limit, you will get the values inside the bracket as 1 by mu minus iq minus 1 by mu plus iq, and after simplification this is minus mu b by h bar square qi into 2 iq divided by mu square plus q square. Now let us simplify the expression. F of theta is equal to minus mu beta divided by h bar square into 2 by mu square plus q square. This is the expression for the scattering amplitude using the first Born approximation for spherically symmetric potential. Now once you have f of theta, you can calculate the differential scattering cross section by taking the modulus of f of theta square. Now we can say here f of theta is proportional to 1 by mu square plus q square. When f of theta is proportional to 1 by mu square plus q square means the differential scattering cross section is proportional to modulus of f of theta square, that is equal to, that is d sigma by d omega is proportional to modulus of 1 by mu square plus q square square. Now what is q here? From the diagram we can see that q is the magnitude of the difference of k0 bar minus k bar, where k0 bar is the incident wave vector and k bar is the scattered wave vector, and the magnitude is 2k sine theta by 2. That is, the magnitude of q is 2k sine theta by 2. Therefore d sigma by d omega is proportional to 1 by modulus of 1 by mu square plus 4k square sine square theta by 2 whole square. Now you can take this 4k square outside so that our d sigma by d omega, the expression becomes 1 by modulus of 1 by 4k square modulus of 1 by 4k square, then within bracket mu square by 4k square plus sine square theta by 2 whole square. Therefore d sigma by d omega can be written as modulus of 1 by 4k square within bracket mu square by 4k square plus sine square theta by 2 whole square. Now we can substitute a square instead of mu square by 4k square in the expression for d sigma by d omega. That is, put a square is equal to mu square by 4k square, so that your equation reduces to d sigma by d omega is proportional to modulus of, it is proportional to modulus of 1 by a square plus sine square theta by 2 whole square, or we can say d sigma by d omega is proportional to a square plus sine square theta by 2 all raised to minus 2. That is, from the given option, option C is the right option.